Happy Friday. We're going to go over our bell ringer for day 44. Notice it says to check Infinite Campus, your current grade, absences, missed assignments, test corrections. Please especially make sure you look and see if you have any zeros. If you have any zeros in for those grades, you need to go back and make sure that you complete what's missing and turn it in, and make sure that we know that you've turned it in. You don't want to go into the 9 weeks with zeros. So go ahead and check those grades. Check your absences. Sometimes Infinite Campus does funny things. So check those and let us know if you have any questions. Okay, next it says our DNA template is TGCACG. And we're going to make an mRNA. Okay, remember the big thing to remember when we're going from DNA to RNA is that there are no T's in RNA. Uracil is going to replace thymine. So if you think you're supposed to be putting a T, but it's RNA, you're going to put a U. So let's take a look. We're going from DNA to mRNA. DNA can't leave the nucleus. It has to have a messenger to take those instructions for proteins out to the ribosomes out in the cytoplasm. So that messenger RNA is going to do that for the DNA. Then it has to copy. It copies just little pieces at a time. Not like replication. It would just take one strand and just copy the little piece of that strand that would be coding for a certain protein. And then it would go out of the nucleus and take that message to a ribosome that would put it together. Okay, so for our DNA, if we have T, T would go with a U, G would go with C, C would go with G, A would go with U because this is mRNA, C would go with G, and G would go with C. And it won't let me type on here, so again, real quick, that would be A, C, G, U, G, C. And notice how we have 2 triplets. That would code for 2 amino acids. Next one says, what is the function of RNA polymerase during this process? Well, it's much the same as it is in DNA replication. DNA polymerase is going to come in and put down those complementary bases and then proofread and make sure they're in there correctly. So RNA polymerase is going to do the same thing for RNA. So the enzyme that makes mRNA, it puts in and it proofreads. So it's going to put in those complementary bases. If there's a G, it'll put a C. If it's a T, it'll put an A. If it's a T, it'll put an A, and so on if we're making RNA. And then it's going to proofread and make sure those are in correctly. The next one says, what is translation? Well, we said transcription is going from that DNA template, those DNA instructions for the proteins, and then copying them to make an mRNA. That would be transcription. Translation will be translating from that DNA language into the protein language. Translation is going to happen at the ribosomes with the help of tRNA, that tow truck RNA I mentioned earlier. Tow truck RNA. Technically it's tRNA, but I call it tow truck RNA because that helps me remember its job. It's going to go out into the cytoplasm. It's going to pick up those amino acids. Remember, the cytoplasm is mostly water, and it's got all kinds of things dissolved and floating around in there. Well, the tRNA is going to have what's called an anticodon, which is complementary to the mRNA section. It's going to be complementary to that mRNA section. It's called an anticodon, and it's going to match up with a specific amino acid. And we're going to talk more about that in a little bit when we learn to read the codon wheel. The translation would be going from that mRNA, those tRNAs, those tow truck RNAs are going to go out and pick up amino acids. And it's going to stick those amino acids together with peptide bonds to make a polypeptide or a protein. So that translation is what's happening at the ribosome. It's going from that RNA to a protein. And transcription was going from DNA to RNA. And translation is going from the RNA to the protein. And where does it occur? Well, ribosomes make proteins, so it's occurring at the ribosome. Translation is making a protein occurring at the ribosome. And nucleotide does not contain which one? when we've drawn a nucleotide several times, it has that 5-carbon sugar, and then we put a line, use a circle over here to represent the phosphate, and we'd use a little rectangle over here to represent the base. So we have a sugar, phosphate group, and base. So sugar, phosphate, base. Sugar, phosphate, base is a nucleotide. So it does have a 5-carbon sugar. It does have a nitrogen base. It does have a phosphate group. Okay, the polymerase was not part of the nucleotide. Remember, polymerase is what we were talking about up here. It's the enzyme that's going to go in and put down those complementary bases and then proofread them. So the nucleotide does not contain polymerase. It does contain a sugar, a phosphate, and a base. The bases of the DNA molecule are held together by hydrogen bonds. They're held together by hydrogen bonds. And they need those weak hydrogen bonds so that you can come in and unzip. We have to be able to unzip that DNA molecule. So either DNA replication can happen or make transcription to mRNA. Either one, the molecule has to be unzipped. So it has weak hydrogen bonds between the bases in the middle. The sides, on the other hand, it's going to be the alternating sugar, phosphate, sugar, phosphate, sugar, phosphate all the way up and down the sides. Those are held together by covalent bonds, so they're stronger. Those sides don't break apart as easily. Those hydrogen bonds can be opened up between those spaces. They can be opened up along here, allowing that polymerase to get in and put in and proofread. And the last one, if one side of the DNA molecule reads TGAACC, what will the complementary side read? Okay, we're making a complementary DNA this time. So T would go to A, G would go to C, A would go to T, A would go to T, C would go to G, and C would go to G. And there it is for you right there. And that's that.